Hello, hi everyone. Welcome to this Student the Brand. This is your Sir. So today we are going to discuss about. Hello, hi everyone. Welcome to the Student the Brand. So this is your Sir. Today we are going to discuss about laws of motion. Laws of motion. Okay. So here you can observe. You can observe. You can observe. Early morning, you want to wake up. You're trying to wake up, but still we can't able to get up from the bed. And so initially, when you want to drag the object, when you want to push the object, we need a lot of force required to displace the object initial time. Yes or no? So when you want to drag the object, when you are carry on, when you want to carry the object, okay. So when you are standing, so if you want to move, okay, so we need a force. And so if fan is rotating, suddenly fan will stop by its own. If fan is there at rest position, by its own it can move. No. Object is placed on the table. Will it move by their own? No. So the object does not move by its own unless external force acting on it. The object does not move from its position unless external force acting on it, unless external agency acting on it. So that is called inertia. Inertia is nothing but tendency of the body to remain same in its state of motion, rest or position. Or state remains stay in its state. Means, so without external force acting on it, the body does not move from its position, from its state. Is called inertia. Is called inertia. There are three types of inertia. Okay, so coming to the laws of motion. Okay, laws of motion. Okay, laws of motion. The laws of motion. Laws of motion. Understood or not? So we are talking about laws of motion. Laws of motion. Clear? So here I said inertia. What is that? Inertia. So how many types are there? Inertia of rest. First one is inertia of rest. Second one is inertia of motion. Third one is inertia of direction. Inertia of direction. So coming to inertia of rest. Unless external force acting on the body remains its state of rest. Stay in its state of rest. Best example, so a book is placed on the table. Okay. So without any external force, the book will not move from the table. And a fan you can see. Without external force acting on the object, the body does not move. Right? So even table also. Without external force, the body does not move. And during exam, without external force of parents, our own it won't start. Okay. Sometimes our friends are required to push, to motivate, not push, to motivate us to prepare for exams. Understood? And do good things. Understood or not? Some external agency is required to move the object. Without that, the body stays in the same state. Here, same position. That is rest. Okay? Understood or not? So, one example I'll tell. So, I'm sitting in the bus. I'm sitting in the bus. Okay? So, suddenly the bus start moving. Suddenly the bus start moving. Then which direction will fall? So our upper portion will stay at rest. Lower portion is trying to move along the bus. So we'll move backward. Understood or not? So when I'm in moving bus. So I'm standing in the bus. So legs are contact to the moving bus. So body is in motion. Suddenly bus is trying to stop. Then we'll fall forward. Because our body is in moving condition, our legs are contact to the bus, so it's trying to stop. That is the reason. So this is all about inertia of rest. And one more example, you can observe the carom. Okay, na? So caroms arranged one by one. Caroms arranged one by one. Okay, the bottom of the carom. So you can see carom board. So the coins are arranged. The coins are arranged. So if you hit the bottom coin, only the bottom coin will move forward. Remaining all coins will stay at the same position. So it falls at the same position. So you can observe. Okay. So these are all examples for inertia of rest. Inertia of rest. And coming to the next one is inertia of motion. So you can observe an athlete. So long jump person, high jump person, he will go far distance and start running from there, and to give motion to our body, to give motion to the athlete body, he will run from far distance, little far distance. Then he will try to jump, long jump. Okay. So then the body is already in motion, then automatically we can able to move forward still little more. Understood? And one more example. So generally people are getting down from the running bus. They have to move in the same direction. In the same direction along the bus. So if they jump and just trying to stop immediately, they'll fall. Because already in running bus, they have to give motion to the body. Then by that, after certain distance, if we travel, if we move, then we can able to stop. That is one example. Understood? And one more example. One more example. So when we are moving the bus, suddenly the bus is taking a turn. Okay? Suddenly the bus is taking a turn. So we'll fall forward or backward according to the bus turns. Understood or not? So it depends. It depends. Okay. So unless external force acting on the body continues in the same state. Whether it is rest or whether it is motion. And one more example, you can see during rainy time, so bike or cycle, you can observe the water droplets moves along the tangential direction. Water droplets moves along the tangential direction. Understood or not? Yes. Okay. So we are moving in a straight line path. When you are moving in a straight line path, So unlike external force acting on it, we won't move another directions. So the finally what we can say, what is the conclusion of this one means? So without external force, the body does not change its position or change its state by its own. By its own, it won't change. Some external agency, some external force is required to move the object from its state of rest, state of motion, state of direction. Understood? So this is about inertia of rest, inertia of motion, inertia of direction. So these are the 3 points. These are the 3 points. Understood or not? I hope it is very clear. I hope it is very clear. Is it clear? Now, next one is force. Force is nothing but a push or pull of an object is called force. A push or pull of an object is called force. A push or pull of an object. Force. Here, two types of forces are there. One is contact force, another one is non-contact force. Okay. Yeah, these classes actually, those who are going to 11th class, I'm taking classes for them only, 11th standard. Okay, so 11th class and for 10th class already it's going on, for 11th it's going on, for 12th also it will going on. So definitely, okay, now 11th class, that is for now I'm taking class on laws of motion. That will be helpful for grade 11. At the same time, those who are attempting JEE and NEET also. Okay, so for both, and it will be helpful for general grade 11 CBSE. Okay, so now let's start. Here you can observe contact force and non-contact force. Contact force, and the second one is non-contact force. Non-contact force. Sir, what is contact force? Contact force is nothing but so the force will, what is force? A push or pull of an object. Okay, so if you want to apply if you want to move the object, we need to apply some external agency. Okay, so that makes the object to move from one point to another point. Okay, opening the door, closing the door, opening the door, closing the door. Okay, carrying the things. Understood or not? So holding the book, moving. Okay, so these all we are applying some force. We are applying some external agency to move the object from one point to another point. So force is nothing but a push or pull of an object. Okay, so here there are two types of forces are there: contact force and non-contact force. Contact force, with the bodies are in contact, then the force will act. That force is called contact force. Best example, friction. Okay, so when we are writing on the board, when we are writing on the paper, okay, so everything. So when we are walking on the ground, so when you are throwing ball on the ground, okay, by contact of objects, so two objects are in contact, then the force will act. That force is called contact force. Example, friction, muscular force. Okay, so these are the examples. Contact force example. Coming to the non-contact forces. Non-contact forces are nothing but without contact. So there won't be any contact required for acting force between the objects. Okay, without any contact also force will act. Example, magnetic force. So you can observe North Pole, if you bring closer to each other, so it won't attach, but still force will act. South Pole, you bring closer to each other. Without contact only force will act. Electrostatic force, gravitational force. Okay. So these are all related to non-contact force. Non-contact force. Without any contact, the force will act. The force will act. Understood? So this is about non-contact force. Non-contact force. Is it clear? I hope it is very clear. So now we will discuss about momentum. So momentum, what is linear momentum? We'll discuss linear momentum. Linear momentum. Linear momentum. Linear momentum. Linear momentum is nothing but, so linear momentum is a vector quantity. So P bar equal to mv bar. P bar equal to mv bar. Mass into velocity. Velocity is a vector quantity. Momentum is a vector quantity. Understood? I hope it is very clear. Clear? So laws of motion, in that inertia of rest, inertia of motion, inertia of direction. Coming to the force, there are two types of forces, contact force and non-contact force. Okay, with the contact only the force will act, that is called contact force. Without contact the force will act, that is called non-contact force. Okay. And the next one, linear momentum. Linear momentum. Linear momentum is nothing but mass into velocity. Mass into velocity. SI unit of mass is kg. SI unit of velocity is meter per second. Okay, so that is the momentum SI unit. SI unit of momentum, linear momentum. And coming to the law of conservation of linear momentum. So momentum will be conserved. Before, say two bodies are there. So M1, U1, suppose I am taking here. So before collision I am taking like this. Okay, so I hope it is very clear. Inertia of rest, inertia of motion, inertia of direction. So let's start. Law of conservation of linear momentum. Law of conservation of linear momentum. Law of conservation of linear momentum. Linear momentum. Understood or not? So that is, if two bodies are there, so I am taking this is body 1. So mass of the body is m1, initial velocity u1, and the next one mass of the body m2, initial velocity u2. After collision, after bombardment, so mass of the body is same, but velocity is v1. So later here mass of the body is m2, v2. So then m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. Momentum before collision equal to momentum after collision. So even recoil velocity of the gun. Recoil velocity of the gun. So before system is at rest completely, this entire term becomes 0 because M1, U1, M2, U2. So bullet and gun both are at rest. After recoil, okay, so here you can take, both are moving. So bullet and gun are moving opposite direction. Understood or not? So that time you have to take. I hope it is very clear. I hope it is very clear. Recoil velocity of the gun. So to find out, we can use this formula. Even kinetic energy also. So law of conservation of kinetic energy. So kinetic energy before collision equal to kinetic energy after collision. Understood or not? So I hope it is very clear. So now next we will discuss about impulse. Impulse is nothing but large force acting in a small interval of time. Impulse, large force acting in a small interval of time. Impulse. So we can take I equal to F into T. Or simply we can say F into T equal to change in momentum. So momentum, just now we discussed mass into velocity. Mass into velocity. Large force acting in a small interval of time. Large force acting in a small interval of time is called impulse. Okay. So I equal to F into T. I equal to F into T. Large force acting in a small interval of time, that is called impulse. So the forces which are acting, impulsive forces. Best example, so cricket batsman, he will hit the ball. He will use his force to hit the ball. So he will use large force. So acting in a small, hitting the ball within a seconds. Okay. So will it large force acting in a small interval of time. So I hope it is very clear. So impulse equal to F into T. So that is nothing but change in momentum. F into T equal to change in momentum. Understood or not? So one check it. One check here. Next one we will discuss about Newton's laws. Newton's first law, second law, third law. Newton's first law, second law, third law. Newton's first law, second law, third law. Newton's. Newton's first law, second law, third law. So what is first law? It defines inertia. So first law defines inertia. So in the starting of the class, I explained. So inertia of rest, inertia of motion, inertia of direction. Mass is the measure of inertia. More mass, more inertia. Less mass, less inertia. Mass is the measure of inertia. Okay. So coming to the next one, Newton's second law. The external force acting on the body. Coming to second law, the external force acting in the body is directly proportional to change in momentum. The rate of change in momentum. The net external force acting on the body is directly proportional to rate of change in momentum. So F equal to K into mv minus mu by T. So K equal to 1. K equal to 1. So then F equal to m into v minus u by T. What is v minus u by T? That is acceleration. F equal to ma. F equal to ma. Understood or not? So I hope it is very clear. Check once here. So Newton's first law, second law, third law. Second law is nothing but the net external force acting on the body is directly proportional to rate of change in momentum. So K equal to 1, F equal to ma. That is second law. First law is about inertia. First law is about inertia. Second law equal to F equal to ma. And coming to third law, every action there is equal and opposite reaction. Every action there is equal and opposite reaction. Equal and opposite reaction. So when you throw the ball, so again when you throw the ball on the wall, again after hitting the ball will come back. Okay. So every action there is equal and opposite reaction. That is Newton's third law. Okay. So next one. So I hope it is very clear. Understood or not? So right from starting onwards, inertia of rest, inertia of rest, inertia of motion, inertia of direction. Next force, a push or pull of an object. A push or pull of an object is called force. There are three types. Sorry, to contact force, non-contact force. Okay. So Newton's laws of motion. So first law, second law, third law. Coming to the Lami's theorem. Okay, Lami's theorem. We'll discuss about Lami's theorem. Lami's theorem. Lami's theorem. Understood or not? Here you can observe. Lami's theorem. So three forces are acting on the particle to make the particle in equilibrium. F1 is acting like this, F2 and F3. So opposite to F1 alpha, opposite to F2 beta, opposite to F3 gamma. Okay. So Lami's theorem is equal to F1 by sine alpha, F2 by sine beta, F2 by sine beta, and F3 by sine gamma. F3 by sine gamma. Understood or not? Lami's theorem. And coming to the next one, weight. Weight of the object. Okay. So weight of the object always acting downward direction. Weight of the object always acting downward direction. So now we will discuss about, so normal reaction will be acting upward direction. Weight. When the object is placed on the table, here you can observe. So here you can observe this the object weight. Weight of the object is acting downward direction. W equal to mg. And normal reaction or reaction force is acting upward direction. Normal force, that is reaction force acting upward direction. Suppose if I am taking, so I am standing in the lift. So lift condition. So this is very, very important. So lift example. There are three cases are there. There are three cases. Case. Okay. First one. So this the lift. This the lift. So weight is acting. I am standing on the lift. So in the lift. Object weight, if you are taking weight of the object, weighing machine. So on the weighing machine, the person is standing if you are taking. Okay, reaction force is acting upward direction. Reaction force. Simply we can take the person is there. Okay, so like this. Weighing machine. So reaction force is acting upward direction. That is R. If the lift is moving with a uniform velocity, or simply we can say lift is not moving, either at rest. So if I am taking rest or uniform motion, rest or uniform velocity or constant velocity, so better we can take constant velocity. Lift is at rest or moving with the constant velocity. So the formula is R equal to mg. R equal to mg. This is a case one. And coming to the next one. So here from F equal to ma we have to take. Always we have to use the formula F equal to ma. Force equal to mass into acceleration. Net force. That is net force we have to take. So this weighing machine. So the person is standing. So reaction force I am taking this R1. And weight is acting downward direction. So weight is lift is moving upward direction. Upward direction. Okay, lift is moving upward. If lift is moving upward direction, then the formula is, so lift is moving upward direction, then R1 minus mg equal to ma. Understood now? R1 equal to mg plus ma, that is equal to m you are taking common, g plus a. Means when lift is moving upward direction, so upper end weight will be more than actual weight. So we experience our upper end weight will be more than actual weight. So if lift is moving downward direction, third case number 3, third case, if lift is moving downward direction, like here. So here weight, so weight is acting downward direction. Normal reaction will be R2. So lift is acting downward direction, downward motion. So downward. Okay, lift is moving downward. Then what about the reaction? That the formula is mg. This time lift is moving downward. That's why mg is greater than R2 than ma. Right? Then so R2 equal to mg minus ma. Then m equal to g minus a. Okay, so we feel lighter. The upper end weight will be less than the actual weight. Upper end weight is less than the actual weight. Is it clear? Is it correct? So let me know. First one, if the lift is at rest or moving with the constant velocity, then so our weight will be same. So upper end weight will be same, actual weight. Then when lift is moving upward direction, so upper end weight will be more than the actual weight. R1 minus mg equal to ma. Then R1 equal to mg plus ma, that is equal to R1 equal to m plus g plus a. More than actual weight. When lift is moving downward direction, okay, so we feel less weight. Than compared to the actual weight. I hope it is very clear. So that's enough. So this is about laws of motion. Right from starting onwards, we discussed inertia of rest, inertia of motion, inertia of direction. Okay. After that, force, contact force, non-contact force, linear momentum, law of conservation of linear momentum, even kinetic energy also same. Okay, so after that, so we discussed Newton's three laws, Newton's first law, second law, third law. After that, weight, and so coming to the lift case, lift condition. I hope it is very clear. So if you like the content, if you like the channel, please do like, share and subscribe to Student the Brand. This is your Shiva sir. So thank you so much for joining and attending and listening my class. So we'll see you in the next class. Thank you.